Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on December 12, 2025, about 3 days ago. It shows that you can train a large-scale text-to-image diffusion model entirely in the feature space of a visual foundation model, skipping a variational autoencoder, yet still reach 0.75 on general eval and 85.78 on DPG bench. The paper is titled SVG-T2I, Scaling Up Text-to-Image Latent Diffusion Model Without Variational Autoencoder. And, as we will see later, the implications for unifying perception and generation are pretty significant. Also, the authors shared an official PyTorch repo. Inside, you'll find the full SVG-T2I codebase, including the SVG autoencoder and diffusion models, training and evaluation pipelines, environment setup, data preparation configs, plus scripts for multi-stage training and text-to-image sampling, along with links to pre-trained checkpoints for direct experimentation. On the SVG-T2I page, you'll find 2.6 billion parameter diffusion checkpoints, multiple autoencoder stages up to 1024 resolution, plus training, inference, and evaluation examples. Figure 1 demonstrates that SVG-T2I already produces high-quality, diverse images across many prompts and aspect ratios. The full collage shows realistic food, portraits, animals, landscapes, flowers, and even painterly tulip patterns, which signal strong semantic control from text. The left column emphasizes natural photos, like wine still life, mountains, a red rose, and a cat. The center column mixes fantasy portraits and a fruit bowl, testing both human detail and composition. The right column focuses on wildlife, flowers, and coffee drinks, so it highlights texture, color richness, and fine-grained edges. Figure 2 explains how SVG-T2I processes text and images together in feature space. The left side shows a single stream transformer block that takes Gemma 2 text embeddings, noised dino features, and a time embedding, then predicts the denoising velocity, which is the direction that removes noise from features. The right side shows the autoencoder, where a frozen dino encoder yields self-supervised features and an optional residual encoder adds fine detail before a decoder turns these features back into pixels. This joint design means the same feature space supports both reconstruction and text condition generation. Figure 2 just showed how the model ties text and visual features together, and Table 1 now explains what data actually feeds those components. For reconstruction, Dataset A has about 1.2 million ImageNet images. Dataset B adds roughly 3 million high-quality realistic images. For generation, Dataset C contributes 60 million general images with diverse captions. Dataset D brings 15 million additional realistic samples, and Dataset E finishes with 1 million high aesthetic images, while the caption sampling scheme balances short, medium, and long prompts across training. Table 5 summarizes how different text-to-image models handle the general eval benchmark, which checks things like object counts, colors, and positions in generated images. The main takeaway is that SVG-T2I reaches an overall score of about 0.75, matching strong variational autoencoder-based diffusion models. The upper block lists discrete autoregressive systems. The middle block covers popular variational autoencoder diffusion models, and the bottom row highlights SVG-T2I as a representation space diffusion model that stays competitive across all subtasks. Table 6 shifts to the DPG benchmark, which scores how well generated images preserve global layout, entities, attributes, and relations. The upper block shows strong, discrete autoregressive models clustered in the low to mid-80s overall. The middle block lists popular variational autoencoder-based diffusion systems that mostly land in the 70s and low 80s. The final row highlights SVG-T2I, which reaches about 86 overall, matching the very best diffusion models despite operating purely in visual foundation model feature space. Alright, wrapping up, 2 takeaways stand out. First, high-dimensional visual foundation model features can act as a powerful unified latent space for reconstruction, perception, and competitive text-to-image generation. Second, this opens a path to simpler, more integrated vision stacks without a separate variational autoencoder. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.